All right, so we are here for round 2 of Unit 3, Unit 3 being our nuclear chemistry unit. All right, so we are going to delve into the role of half-life and how we can use things like half-life to estimate the age of something or to figure out how much of something will be left after a certain amount of time. Very useful skill to have. All right, so first of all, is what radiometric dating is the use of radioisotopes and their associated half-lives to figure out how old something is, if it had a certain amount of radioisotope to begin with. Okay, so first of all, we talked about alpha decay and beta decay and positron emission, electron capture, all these little processes that occur to change the nucleus, transmutate it into something stable. All right. One of the things we haven't discussed yet is does that happen randomly? Is there some order, rhyme, or reason to it, etc.? And so, as it turns out, it's a random process based on probability. All right. It also has to do with just how quickly or how common it is for a radioisotope to actually go through that decay process. All right. First of all, we need to understand that decay process takes time, right? It occurs over a certain amount of time. So not all radioisotope atoms are just going to decay at one time, right? That'd actually release a lot of energy all at once. It'd be kind of a bad news. But it's actually, often it can be a very, very slow process. So for some cases, it's really, really fast. It kind of depends on the isotope. But they decay over time and not all at once. All right? And the rate is different for different radioisotopes. And in fact, no two radioisotopes have the exact same rate of decay. All right? And so when we measure the rate of decay, we usually use the term half-life. Okay? So a half-life is a measurement of time, by the way. And that time could be anywhere from seconds to millions of years. All right, so it just kind of depends on what unit we use for half-life. It's not a constant. We could be measuring that in microseconds, really, all the way up through tens to hundreds of millions of years for a half-life period. It just depends on the isotope. Okay, recognizing that half-life is a unit of time. All right, so why do we call it half-life? And that has to do with the fact that a half-life is a measurement of the time required for 1/2 of the original isotope to go through its decay process. Okay? So, time required for 1/2 of the radioisotope to decay into its products. And that is the half-life. Alright. So, here's a common example. Sometimes you hear about carbon dating, right? Carbon dating is a type of what they call radiometric dating, by the way. It's just one way we can date things. Sometimes they use carbon dating in place of radiometric dating. It's not entirely accurate. Okay? So we know carbon-14 is a radioisotope, and we know that it will decay into nitrogen-14 via beta emission, right? So you got 14 over 6C is going to become 14 over 7N plus an electron. All right? So there's our beta emission. Okay? But first of all, remembering that atoms are really small, and we're going to have a whole bunch of those atoms in one place. Right? Very, very large number to make a very small sample. But the time required for half of the carbon-14 to decay into nitrogen-14 is about 5,730 years. All right? Now, if a sample originally contained 100,000 atoms of carbon-14 and now contains about 25,000 atoms, how old is that sample, right? So this is a way that we can use half-life and radioisotopes to estimate the age, with a certain degree of uncertainty. All right? So the formula we use for that is the age of the sample is equal to the half-life, notated as T1/2, times the number of half-life periods, right? Which is our value there for N. So the number of half-life periods is N. The half-life itself is T1/2. All right. Now, we don't really have enough information just yet, or enough. There's some other little side calculations we have to do to actually tackle this problem. Okay, so this is going to seem really complex to you guys at first. It really isn't. It's just kind of plugging values in based on what you know and then solving for what you don't know. All right. So we have enough information here to actually figure out how old the sample is. The trouble is we can't just plug numbers into this equation yet, right? We can plug the half-life in. We know that number. We don't really know what n is. Now, some of you guys might be able to figure that out pretty quick, but we'll come back to that in a minute. Okay? So, some variables to consider. First of all, the age, or t, often. Okay? I usually will just write it as age, though. We have the half-life itself, which is going to always be written as t1 half. The original amount of isotope. So, this is the equation I just showed you, right here. Right? Sometimes, in order to answer or use this equation, we need to use this one first, all right, to solve for our n. Okay? So in the case of that carbon-14 example, we don't know n, so we're actually going to use this one first to solve for n. I'll show you guys how to do that momentarily. All right? So Mi, our mass initial, or the amount initially, is the original amount of isotope. The Mf is how much we have at the end of a certain period of time. Or maybe it's how much we have now if we're trying to figure out how old the sample is. Okay? And n is the number of half-life periods. So, I shouldn't say usually, always. So we'll give you enough information, right, that you can with given variables so you can calculate the variables you're not given. And sometimes it might mean using this equation first to get n, and then using n from there in that equation, or maybe getting n from this equation and figuring out something down there. All right? So it's going to involve sometimes two different equations to get our calculation done. But you'll always be given enough to work with. Okay? So let's take this into account. I'm going to walk you guys through this carbon-14 question, all right? But we need to understand the relationship between variables and how we can use some to figure out the others, okay? So here's our carbon-14 question again, all right? So we know certain values. We know the half-life for carbon is 5,730 years. So I'm just going to write these out. T1 half equals 5.73 times 10 to the third. All right? So I know that value right there in that equation. All right? Originally contained 1 times 10 to the fifth atoms of carbon-14. That's the original amount of radioisotope. So that is that Mi value. So I'm going to put a, glitchy little check mark next to Mi, and I'm going to say Mi equals 1.00 times 10 to the fifth, and that's years. This is atoms. So, quick thing to point out, by the way, the initial amount of isotope, right, is not always going to be given in atoms. It might be given in grams. It might be given as a percentage. All right? Either way, as long as our Mi and Mf are the same unit, we can do that. All right? So, the sample originally contained 1 times 10 to the fifth atoms of carbon-14, right? Now it contains 2.50 times 10 to the fourth atoms. So that, how much it actually has now is our Mf. So I'm going to write that variable down. Mf equals 2.50 times 10 to the fourth atoms. Okay? So, the variables here that we know are the half-life, we know Mi, and we know Mf. All right? So what we don't know yet is N, and we don't know the age. All right? Whoops, sorry about that. So, how then can we go about figuring out the age of this sample? All right? Because that is what is actually being asked of us right here, right? It says right here, how old is the sample? So we are trying to figure out our age, right? But in order to do that, we need to know N. Okay, so from your algebra experience, right, which of these two equations is going to help us initially solve for n? All right, so you should have noticed that this equation right here, we know everything except for n, right? We know mf, right, which is 2.50 times 10 to the fourth. We know mi, which is 1 times 10 to the fifth. Okay, the only thing we don't know is n. All right, so the signal there is that's probably the equation we want to use. Now, in the top equation, we don't know the age, we don't know n. The only thing we know is the half-life, and that's not enough to solve that equation. All right, we do have enough to solve for n here. Then, once I know n, I can substitute that into that equation and solve for the age. Okay, so you're seeing here, I wrote all my variables out first. All right, and I wrote my unknowns out next to it. And that gives me a kind of a more condensed version of the data that I need to use to figure out which equation to start with. Now, if you guys weren't watching me do this, I would probably still do that because it's going to help me avoid mistakes. Not because I'm not smart enough to figure it out, but it's because I like to write things out to avoid mistakes. All right, so let's solve this bad boy. I want to figure out the value of n, the number of half-life periods. Okay, I'm going to use this equation right here to solve for that. So I'm going to substitute my values in. My mi is 1.00 times 10 to the fifth. All right, so that value times 0.5 to the n equals 2.50 times 10 to the fourth. All right, now I'm going to do simple algebra. I'm going to divide both sides by 1 times 10 to the fifth. So I'm going to get 0.5 to the n equals 0.25, or in scientific notation, 2.5 times 10 to the minus 1. Okay. Now, most of you guys have been taught how to solve for an unknown exponent. If you're in Algebra 2 right now, maybe you haven't quite gotten to that. It's not difficult. I'm going to write down a little symbol that you may or may not be familiar with, but all it amounts to is punching a button on your calculator. That's really all it is. All right. So when my unknown is an exponent, all right, I'm going to either use a log function or a natural log function. I like to use the natural log function for whatever reason. I think that's just how I was taught to do it. But the log button works just as well in this case. So what I'm going to do is I'm going to rewrite this equation, right, to make use of the log or natural log function to solve for n. And all I'm going to do is I'm going to bring the n down. So I'm going to write n times the natural log of 0.5. And again, the ln, that natural log right here that we see, is just a button on your calculator. Okay? So now I've separated my n out as its own little variable instead of having it be an exponent. So on the same side, I need to do, or on the other side, I need to do the same thing. I'm going to need to take the natural log of 0.25. Okay? So, again, to bring this n down and make it its own little variable that's not attached to that 0.5, right? I brought it down, but in order to bring it down as a multiplier, I need to use this natural log button on my calculator on both sides of the equation. All right? So now I can solve for n by going the natural log of 0.25 over natural log of 0.5. All right? And when I do that, I get a value that is equal to 2. So n equals 2. So that tells me that to get from this number of atoms down to that number of atoms, I went through 2 half-life periods. Okay? So now, I know n equals 2. So I can now substitute the 2n to my age equation. So I now know that n is 2. So I'm going to go to this equation right here. Age equals 5.73 times 10 to the third, right? Which is that value I wrote down over here for t1 half times 2. Age equals, 5.73 3 times 2. 1.15 times 10 to the 4th, or about 11,500 years. All right, and you may have noticed if you punch that on your calculator, it got 11,460. I'm using sig figs like always, and there is my age. Okay, so that's one example. We will go through several more together in class tomorrow. All right, so if you can walk in though with these notes and having some basic understanding for what the formulas are and at least what the different symbols mean. Maybe you got a little lost in the natural log side of things. That's okay. But if you walk in the door with at least this stuff in your notes, I think will be a good starting point to take it from there. All right. See you tomorrow.